Oh, you know what? Okay, let's talk about a slope field. I also remember that I'm going to have issues drawing on this. So, don't mind as I try to pull something up. Slope fields.
Could you close the blinds a little more?
Yeah.
Is that, like, the
I
most-
really like the sunshine, and so...
there's a
Yep.
He looks so sad. I just like to see. I also like the sun.
Tell me about a slope field.
It's a
Field
field of
slopes.
line.
Okay.
They're like this. Weather is
Oh!
just slope fields.
Okay, weather. Interesting.
Vectors?
Vectors.
I don't know. That's a good question.
Line. A lot of them.
What are those little lines representing?
Slopes.
Okay, so we have a graph that is representing all of, so you know how like we got new computers?
Yeah.
Everything changes when you get a new computer.
I don't know how to use this. Mr. Price is very upset about it. All the time his PowerPoints look bad. And he...
Yeah, like look, that looks terrible, but whatever. Okay, so a slope field, we're going to describe because we know what a differential equation is. So a slope field is a graphical general solution to a differential equation. Okay? Now, when I talk about a differential equation, okay, I know that we haven't officially, thank you, talked about it here in this class. But if you have the derivative, getting back to the original function would be solving a differential equation. All right, well, we have all those plus c's, right? So our slope field is giving us an idea of what is happening for any curve with whatever plus c is going to be. Okay. So let's just remind ourselves how this works here. See, my scroll bar is right here, like on the edge.
Not helpful there.
It is not. Okay, so we're going to draw a slope field for x squared. Okay. For each coordinate you see on the grid, you need to plug that coordinate into the derivative. I gave you a pretty easy one to start with. Our derivative is x squared, which means does the y coordinate? No. But I'll just remind you that we need to evaluate the derivative at coordinates to identify what our slope is. So the coordinate 1, 1 would have a slope of 1. Itty bitty tangent line. Okay? I love it.
Yes.
You guys go over those all day?
Yeah.
Yes.
Okay. And you will too.
I also got candy.
Oh,
That's the fun part.
like big candy.
Yeah.
Like,
Actually, it's just individually wrapped ones inside of this.
but
so
you
there's
didn't get
more.
just like one little one.
No.
Nice. Okay. What's the slope at 1, 0?
One.
How about 1, 2? What is our slope at 0, 0?
0.
0, 1. Two, 0. We had to think about that one for a little bit. Negative 1, 0, negative 1, 1, negative 1, 2. Those are all going to have slopes of positive 1, and I've been drawing them negative. Positive 1, sorry. I was thinking about the number negative 1, but I knew the slope. Okay? And then negative 2, 0, negative 2, 1, all of those are going to have slopes of positive 4. Okay? Do your best to differentiate between the different slopes. Okay? Going back to your weather map comment, who made that comment? Okay. Going back to our weather map comment, okay, kind of looks like a wind map almost, right? What do all of those little itty bitty tangent lines, if we like follow, whatever, if we follow the wind, what do those look like? Okay, why would it look like a cubic function?
Because the derivative is a quadratic.
The derivative is a quadratic, so our original function would be a cubic of some sort, okay? And we have all sorts of different cubic functions, because when we do the differential equation, we would have that plus c, so we have all sorts of different options. This doesn't represent everything, but it at least gives us a graphical representation of the different things that we can have. All right? So, I would like you to take some time and work on this slope field for me. And then we'll talk about, don't do the initial condition yet, I just want you to work on the slope field. Okay? Feel free to work together, compare slopes, but I need you to take all those dots. Y prime is x plus y. They all have just like different forehead things.
Yeah.
You don't like it? Well, it has some like pattern to it, right?
That stuff's us today.
What are you noticing about these slopes? Anything? No observations?
What was the tangent? Or like an asymptote.
Okay, you see that it's kind of like an asymptote looking thing there. Any like patterns?
Like, yeah, it's like, and
Shifts
that
on over.
slant, they all have the same slope.
Okay, if we go at a diagonal, we have slopes that are the same, right? If we have x plus y, all right, we're going to have some patterns there. Kind of like we had patterns with x squared, since it solely relied on x, we had some vertical patterns. If a differential equation solely relied on y, you're going to have some horizontal patterns, okay? So x plus y, we have this diagonal pattern happening, okay? You've noticed that line, right? Yes, it is acting like an asymptote for your slope fields, okay? So when we go and pick the initial condition 0, 1, okay, we know that at 0, 1, it's going to have a slope of positive 1. It's probably not going to encounter any of those other tangent lines that we have drawn up there, but we know that the wind's going to blow it in a certain way, all right? You see that this diagonal right here all has slope 0, so we know that it is going to have a slope 0 when we encounter that diagonal, okay? We also see that this looks like an asymptote So we are going to have to approach that asymptote. And these get steeper and steeper and steeper and steeper, and so our curve will as well. Thoughts? Okay. Kind of a nice way to ease into a new chapter. Whoa, whoa, whoa. Okay. So, our next, okay, we're going to do two different matching scenarios here. Here we're matching with the general solution. If I'm matching with the general solution, will my equation match the graph?
No, the derivative of your equation.
I agree with what Joe said, yeah.
The
Why?
graph is gonna,
Because it's like the example, that's the derivative way. And I'll show you the general shape of the function because you're graphing the slopes.
Okay, we're graphing the slopes of the derivatives, so our general shape should look like our original equation, our function, right? So what does this look like?
Straight.
It looks like, fair enough, it looks like 3. But specifically, since we're at 0, 0, it looks like sine, doesn't it? Okay, so sine goes with this one. Okay, what about this? What does it look like? Looks like a cubic function. Okay, that one, not as hard on the brain. Below, I have you matching the slope fields with the differential equation. So I'm giving you the derivatives that you need to match to your slope field. Okay, so I'm going to give you 2 minutes to discuss with your pod which ones you think match where. Okay, and I will call on you to report, so you better talk to each other.
F, I feel like is EDX because it's like one graph.
Six is D.
F is definitely one.
Yeah. And then I feel like is A3 because you're doing what yesterday. With 5 BC.
I think 5 is
No wait, I meant 6. You know what I mean. I was gonna be so oh wait.
I think 2 is C.
Yeah. If I could read, that would be helpful.
Mm.
So bad. Whatever they're called. I don't know what they're called. I did at one point. English. Yeah. I'm like, that's not. Then I'm like, high parabola. Like, it's just mixed words together. I feel it.
Give me a thumbs up if you're done. Okay, so you ready? Oh, first I should have said this. The speaker of your group will be the person with the biggest feet. Determine who that is. So like shoe size. Shoe size for my co-ed group. Shoe size.
Left side.
All right.
Okay. All right. This group.
Yes.
Jackson is your representative. What matches? Hey, listen. What matches with A?
Number 3.
Can you give me like what you looked for to match those up?
Like it being the same for each y value, so you know there was only a y in the derivative.
Okay,
That's the only one.
and that was the only one. Okay, I also like that horizontal line at 2, right? So it had to be 2 there. All right. Over here.
For which one?
Are you the speaker?
Yeah.
You're the representative. B.
For B, we said it was number 4.
Okay. And what made you say that?
Well, the graph is at everywhere that it only is influenced by x because at every 0 it's 0.
Okay.
And so on, and also it looks like a quadratic function and x is a derivative of a quadratic function.
All right. Sounds good. Over here. What matches with C?
C is 2. That's what I meant to say.
Okay. I was like, we just said this was 4. Okay. And what made you pick 2?
It's the one I didn't understand the rationale for. We did all of them and then that was the last one.
That was the last one. That was process of okay. That is not a bad thing. Okay. We'll come back to C and talk about it. D.
6. That's what we chose for you.
And what made that one jump out to you?
It was the only one that fit the form of a sine. So
'Kay.
Sine, cosine.
Sine,
So the
cosine,
one
they
that
go
made
together.
sense.
Okay. Your number was fun. Joe? E.
E, 5, because there's an asymptote again where x and y subtracting each other.
Okay. Hey, yeah, good. We got that diagonal symmetry again. Okay. And pod 4 again, or I guess my 4th pod, your pod 7, but whatever. F. What made you pick? Well, what's the only one left? One. And why'd you pick it?
Because in 0 it's 1.
Okay. Also, what's the derivative of e to the x?
Yes!
Right? It's gonna look the same now whether it is derivative or not. Okay? Here, this one, when we're dividing by x, things that I would look for, when we're dividing by 0, we're going to have undefined. So anytime y is 0, we have undefined, right? Anytime x is 0, we'll have horizontal. Those are things that I would look for there, as opposed to, like, when you're doing your process of elimination, that works as well, okay? All right. So, this is only a part of a free response question. Okay. So let's go ahead and talk about it. Let's find our slopes here. First of all, we know that all of these slopes are 0. And we know that all of these slopes are 0. That would probably be worth 1 point on the exam, all of your 0 slopes, and 1 point for all of your non-zero slopes. Okay, so we would have like slope of 1/2, slope of 1, slope of 3/2. Right? Slope of 1, -1/2, 1, -3/2. 1/2, 1, -1/2, -1, -1, -3/2. Okay, that's what that slope field's going to look like. I know that we can plug in numbers and determine slopes, so I just wanted to fill this out quickly so we can get to the new stuff. Okay, but I do want to remind you what we can do with these. Okay, and actually having the slope field is really going to help us with part C. Okay, so writing our tangent line equation through 1.1, what is our slope there? 1/2. So our tangent line equation would be this. Okay. Remember, tangent lines do help us approximate. All right. So if we approximate f of 1.2, that means we're plugging in 1.2 for x. What do we get? 1.2 minus 1 is 0.2. Cut it in half. 0.1, add the 1 over. Okay? Here's what I like. Instead of taking the second derivative to determine this, okay, because, I mean, we can do it, but it would be a little bit of work. We have the slope field. Is this tangent line approximation going to be an under or an over approximation? Raise your hand for over. Raise your hand for under. Okay, I see under approximations more than I do over approximations. Okay, Hannah, why would you say under?
Because where it is on the graph, it looks like a mid type of thing, so it looks like the way you would draw it,
Mm-hmm.
and then so it would go under.
Okay, so you're saying that this is going to fit under our curve. What graphical property, using some calculus words, would we say that that curve would have right there?
Wait, it'd be concave up.
There, that's what I'm
Okay.
looking for. Okay, so since we're concave up, we know that it's an under approximation. Okay, our tangent line is going to sit underneath. Okay, I'm not going to write it all out, so I want to save some time. But since we can tell that that is a concave up part of the curve, or that solution would be, then our tangent line is sitting underneath. Okay, so here's the deal. This one, you know how to separate variables and solve them. We'll review it tomorrow. We can separate variables and solve for that solution. Here, we cannot separate x and y and take the antiderivative because x and y are being added together. Okay? So how do we determine anything about our original solution without being able to do the calculus? Okay, we have to find other ways. So to figure out what this looks like graphically, we have our slope fields. Okay? To approximate values on this solution, we have what's called Euler's method. Okay? First of all, a tangent line approximation is fairly accurate, but Euler's method is more accurate. Okay? It's a way for us to be more accurate in our estimations. Okay? So, what we're going to think about, and I'm not going to make you read all of that stuff, but it's there to refer back to. I want you to think of kind of like walking on a tightrope. And what we're going to do is we're going to adjust our path along the way. So what Euler's method does is we pick a coordinate and this is like super zoomed in, okay? We take a coordinate and we find its tangent line, okay? And then we take a step on that tangent line, but not very far. And we evaluate, okay, from here, what would the slope be of our new coordinate? And we find that tangent line. And then we take a step on that tangent line. And we reevaluate the slope to make a new tangent line. And we do that over and over and over again. Okay, so instead of this blue tangent line, this is my blue marker, but that didn't work out. Kind of forgot that. So instead of that blue tangent line, the further we get away from this original coordinate, the less accurate we are, right? But using Euler's method to keep adjusting our tangent lines, we stay closer to the curve for our approximation. Okay? That is what is going to be happening with the mathematics that we do. So, you are going to have to determine how many steps you're going to take. How many itty-bitty tangent lines are you going to adjust and walk on? Okay? Number of steps, n. Pretty consistent with what we've done before. Okay? You're going to begin at your coordinate. You're going to evaluate the slope. Okay? That's what that is. You're going to evaluate the slope. Then, okay, we know that slope is change in y over change in x, correct? Well, if we multiply the delta x over to the m, that gives us our change in y. So that's what we're going to do here. We're calculating the change in y by taking our slope times our change in x. Okay, and that'll give us a new y value, which we will then use again to reevaluate the slope and move along. Okay, so we're going to fill out this chart over and over until we've taken enough steps and we've come to the coordinate that we need to approximate. Okay? Questions before we actually do the work? Okay, so we need to know how many steps, and we need to know what we're approximating along with the differential equation. All right, here we go. Okay, so we'll have time, I think, to do both examples. All right, in example 1, how many steps are we taking? We are taking 2. Okay. We are beginning at 0 and we're ending at 0.8. Okay? Now, when we talk about, oh, that's so much better. When we talk about delta x, we're going from 0 to 0.8 in 2 steps. So each step, we need to take 0.4 so that we stretch the interval that we need to. Okay? Just like we did, what was that, with Riemann sum approximations, right? B minus A over N. Someone actually likes it. All right. So now we're going to fill out our chart. X, Y, slope, delta Y, new Y. Okay, so we begin at, is that 0, 5? Begin at 0, 5. When we go up here to our differential equation, what is our slope? Okay. If we take our slope times delta x, what do we have? Okay. So if we take our change in y, negative 0.8, we started at y of 5, our change in y is negative 0.8, we are now at, I'm positive 5, did I say negative? 4.2. Okay, so we are now at the coordinate 0.4, 4.2. Where'd that 0.4 come from? Okay, our change in x is 0.4, so we tack it on. Okay, so now we need to evaluate the slope for our new coordinate, 0.4, 4.2. What would that give us? Okay, and negative 1.6 times delta x would give us negative 0.64, which means our new y, so we started at a y of 4.2, our change in y is negative 0.64, so we're at 3.56. So when we start making our next row, we add our change in x. Here is our new y. Hey, that's what we wanted, right? That's what we were looking for. F of 0.8 is approximately 3.56. Isn't that fun? Okay. Now this is one that we could actually solve using a differential equation, right? If dy dx is x minus 2, then wouldn't y be 1/2 x squared minus 2x plus c? Right? And if we had an initial condition of 0, 5, then we could easily solve that. Okay. If we plug 0.8 into the actual equation, we get 3.72. 3.56 is pretty close. Okay. So, okay. Let's also do this. If we were to just write the tangent line equation, we would write y minus 5 equals -2 times x minus 0. What if we plug 0.8 into this? Can somebody calculate that for me? Be 3.4?
Yeah.
Okay, so you can see we're closer with our Euler's method to the actual value than we are with this. How could we be more accurate? More steps. The more steps we take, the closer we are going to be to the actual value. Okay, so 2 steps, there only wasn't that. So let's see what happens here with our next example. How many steps do we get to take here?
5.
5 steps. Ugh. Okay, so what I want you to determine for me is the delta x. Determine for me, please, the delta x. Darby, what's our delta x?
-0.3.
How'd you get that?
1.5 minus 3 over 5. 1.5 divided by 5.3.
Why did you choose 3?
Because, I was looking at the wrong number. -0.1.
You looked at the y value instead?
Yeah. Yeah,
Okay.
the y was first. It really tripped me up.
Sorry about that.
It's okay. It's okay.
All right. So we're gonna delta x is -0.1. All right. Do you agree that 2x minus y, that is not a differential equation that we are equipped to solve? Okay. So approximating 1.5 is something that Euler's method is going to be the most accurate with. Okay. Now, why is delta x negative?
Because we're moving backwards.
We're moving backwards. Okay, we start at 2, we're going to 1.5. So, our chart, okay, and I will warn you, like the AP test, if you ever to look at like answer keys, they probably won't make this chart, but their math is the same. Okay, some people use this chart, some people use the math without the chart, but I think this is a nice way of organizing it all, especially if we have to do multiple steps. Okay, so we start at 2, 3. What's our slope? 1. 1 times delta x is -0.1. So our new y is 2.9. Okay. Our next coordinate, Annalie, our next coordinate would be what? What would we write right here? What's our x? How do we figure that out? Okay. Go back up to here. So our first example, we went from 0 to 0.4 to 0.8. Right? Oh. How do you get that?
2 minus 0.1.
Okay, our delta x is -0.1, so we need to add that to each of our x's. Okay? All right, what's our slope for 1.9, 2.9?
0.9.
Okay. When we multiply that by change in x, we get negative 0.09. So our new y is 2.81. Okay. So our next coordinate is 1.8, 2.81. Okay, so this is our third step. Okay, probably gonna need a calculator to do some of this, right? I mean, you can do it without. It just might be a little bit of a headache. What is our slope? So our 0.79 times negative 0.01 is our change in y. Add that to our old y, old news now, we get 2.731. Victoria, you've done Euler's method. Is this how you did it, or did you do it?
I did a slightly different chart. I did x, y, dy, dx, and then delta x, dy, dx for the headings.
Oh, okay. But you use the chart.
Oh, yeah.
I love it. Okay. All the way from Virginia, she learned the chart.
Love a good chart.
Okay. So our next coordinate is 1.7, 2.731. Anyone have the slope for me?
0.669.
Okay. So when we multiply that by delta y, we get negative 0.0669. Tack that on to our now old news y, 2.6641. Yes. Okay, we've done 4 steps. This is our last one. So we have 1.6, 2.6641. Our slope becomes
0.5359.
so our delta y is negative 0.05359, and our new y becomes 2.61051. Okay. If we were to move on, now I know that we've done 5 steps. Let's talk about what we have found. If we go down our chart with our x's, our next x is 1.5. Our y value is 2.61051. That is the coordinate we were going for. Okay? I don't want us to get into the habit of, I know how to do the math, but I'm not sure how to read my answer, right? So if we have 5 steps, you should have completed 5 rows, and then the beginning of your 6th row is essentially the coordinate that we've reached. Okay. All right. I have a worksheet for you. So your worksheet, 4 slope fields, 6 matching, 4 more matching, couple multiple choice questions, and then a couple Euler's method. On the back is a free response. You get to go through.
The only thing we know is this last part.
Everyone say hi, Gabe.
Hi, Gabe.
Now you'll hear that on the video.
Hi, Annie.
Oh yes, hi Annie.
Hi.
Hi, Annie. We love you.
Code word.
What?
Code word. Shout out a code word.
Watermelon.
Pineapple.
Pineapple was what I was thinking. That's so
Oh,
weird.
yeah.
That's so weird.